Imagine you are teaching a student. They give a wrong answer. To improve, they need to know not just the correct answer, but also what they did wrong. Neural networks face the same challenge. After making a bad prediction, they must identify which weights caused the error and how those weights should change. That's exactly what backpropagation does. It is the learning algorithm that allows neural networks to learn from their mistakes and improve with every training step. Let's see how it works. Every learning cycle begins with a prediction. The neuron combines inputs, weights, and bias to produce an output. We then compare that prediction with the actual value using a loss function. The loss tells us how wrong the prediction is. A larger loss means a worse prediction, while a smaller loss means a better one. At this stage, we know the error exists, but we don't yet know which weights caused it. That's where backpropagation begins. To reduce the loss, the model needs guidance. That guidance comes from gradients. A gradient tells us how the loss changes when a parameter changes. Think of it as the GPS of learning. If the gradient is positive, the weight should decrease. If the gradient is negative, the weight should increase. And if the gradient is close to zero, the parameter is already near an optimal value. Gradients tell the model exactly how to improve. The loss does not depend directly on a weight. A weight affects the weighted sum, which affects the activation, which affects the prediction, which finally affects the loss. To connect a weight to the loss, we use the chain rule. The chain rule breaks a complex derivative into smaller local derivatives. By multiplying these local gradients together, we obtain the final gradient for each weight. This allows error information to flow backward through the network, and that's why the algorithm is called backpropagation. Once gradients are computed, the network updates its weights and biases using gradient descent. Parameters that contribute more to the error receive larger corrections. Parameters that contribute less receive smaller corrections. The cycle then repeats: predict, calculate loss, backpropagate error, update parameters, and repeat. With every iteration, the model becomes slightly better. Over time, these small improvements lead to powerful learning. Let's recap the learning process. First, the network makes a prediction. Second, a loss function measures the error. Third, backpropagation traces that error backward. Fourth, the chain rule computes gradients. Fifth, gradient descent updates the parameters. And finally, the process repeats until the loss becomes small. At its core, backpropagation is simply the efficient application of the chain rule to calculate gradients. Yet, this simple idea powers nearly every modern neural network. Now let's begin with the implementation of backpropagation. So here we are going to implement backward function, which will take x and w as arrays and b is the scalar bias, whereas y true is the true target value, and we'll be using forward function, which is equal to dot product of x and w plus bias, and then we'll be calculating y hat, which would be equal to sigmoid of z, which means we will be using sigmoid as activation function. Then we would be calculating loss using this formula, and after that we will be returning this. So what this means is dl by dw is gradients of the loss with respect to weight, and dl by dv means gradients of the loss with respect to bias. So let's start with the implementation. Let's begin by calculating z and y hat. So z equals to np dot x w plus b, and after that we have to calculate y hat. So y hat equals, here we have to write sigmoid function. So sigmoid function is 1 upon 1 plus exponent of negative z. After this, let's calculate error. Error equals y hat minus y true. After that, let's calculate the derivative of sigmoid. So derivative of the sigmoid would be sig deriv equals to y hat times 1 minus y hat. So this could be calculated using the mathematics, using calculus basically. And after that, let's calculate delta. Delta is equals to error times the sig deriv. And after that, we will be calculating dl by dw, which is np dot round. We are rounding because the question mentions we have to round it to 5 decimal places. So delta times x round to 5 decimal places, and then dl by db, which is equals to np dot round, or just round because it's just the number, and then float of delta, and then 5 because we want 5 decimal places, and then return it as tuple. If you want to go through the formulas of dl by dw and dl by db, you can see in the question description, it's given here. So as you can see here, the gradients of loss with respect to each weight is this, and the gradient of loss with respect to bias is given here. So yeah, let's try and run it. So a single test case has passed. Let's submit it and see it passes all test cases or not. And that's how our implementation is done. And that's the intuition behind backpropagation. A neural network learns by making predictions, measuring mistakes, tracing those mistakes backward, and updating its parameters. This single idea is what enables modern AI systems to improve over time. In the next video, we'll see how backpropagation extends beyond a single neuron and works across multiple layers of a neural network. Thanks for watching, and I'll see you in the next one.